Swayam Prabha. Digital India. Educated India.
So let us use this formula to show that this is actually 0. So keep this 4 by 4 matrix at the back of your mind to see what is going on. So suppose that AJ and AJ plus 1, these two adjacent columns are equal. Okay. Then I look at the submatrix A1I. A1I, so in this 4 by 4 case, there are 4 such matrices: A11, A12, A13, A14. Okay. So if I look at A11, A11 will be this matrix. I delete the first column and the first row. Okay. Then this matrix is a 3 by 3 matrix, and original matrix has second and third column equal. So the second and third column of this are also equal. So determinant of A11 is 0. Okay. Yeah. Now the general statement for this, for n by n matrices, is that A1I, if I choose the submatrix which is obtained by deleting the first row and ith column, will have equal columns except when I equal to j or I equal to j plus 1. Yeah. So here I was equal to 1 and it was not equal to 2 or it was not equal to 3. Then when I look at this submatrix A11, it will continue to have 2 identical columns. So A1I, this submatrix, will have equal columns except when I equal to j or I equal to j plus 1. Because when I equal to j or j plus 1, we will be removing one of these columns to calculate A1j or A1j plus 1. Yeah. So A1j and A1j plus 1 may not have identical column, because one of the AJ or AJ plus will be removed. In this submatrix, jth column is removed. In this submatrix, j plus first column is removed. Okay. But as long as I is not equal to j or j plus 1, A1I will have identical columns, and therefore its determinant is 0. Yeah, its determinant is 0. Okay. So we substitute these values. Yeah. So FA will have only 2 terms left in this: A1j times determinant of A1j, and this A1j plus 1 times determinant of A1j plus 1, and the sign is here is minus 1 to the power j plus 1, here sign is minus 1 to the power j plus 2, because the other determinants are all 0. So I have these 2 terms left over. Yeah, but A1j is the entry in the first row of jth column, and A1j plus 1 is the entry in the first row in j plus first column. But jth column and j plus first column are identical. Yeah, so A1j is equal to this. Okay, this is equal to this, and so AJ is equal to AJ plus 1. That says A1j is AJ plus 1, and also A1j and A1j plus 1, they are identical matrices. Yeah, because when I remove jth column or j plus first column, I am left with the same matrix. So one of AJ or AJ plus 1 is there in one A1j or A1j plus 1, but they are same matrices. Okay. So these 2 terms, they just differ by a negative sign, and therefore f of A is 0, and therefore f of A1, A2, An is alternating. Is that clear? So I wrote the expansion of f by the first column, by the first row, and I want to show it is a determinant function. This is determinant of the matrix. To show it is determinant of the matrix, I need to prove it is alternating, multilinear, and normalized. Normalized property I showed. This is the alternating property. Multilinear property, yeah. Multilinearity of f is left as an exercise to do this. When a equal to I, by induction, f is 1. So you use this formula and please prove the multilinear property. It's a good exercise, straightforward from this formula, that this is multilinear. Okay. We have proved existence of determinant function. This is expansion by the first row, and exactly same proof will be can be written if by, and you can write a formula by expansion by any other row. Okay, any other row and any other column. You have to be careful about the signs. The signs, if I use aij anytime, then the sign which will go with this will be 1 minus 1 to the power I plus j. So suppose I expand by the second row. Okay, I want to expand by the second row. Then it will be minus 1 to the power the first the entry in the first row and first, I mean, the entry in the second row and first column. Okay, second row and first column. Determinant of a to 1, then the sign will be 1 plus 2. Then I look at the next entry. Next entry is a to 2, and the sign will be minus 1 to the power 2 plus 2, and determinant of a to 2, and so on. So you have to be careful about copying this formula for determinant function which is obtained by fixing any row or any column. Okay, the signs matter here. So therefore we have many formulas for determinant, but we have proved that determinant function is uniquely determined. So whether you expand by rows or columns, it is the same. Okay, let's look at determinant of elementary and upper triangular matrices. So I introduced 3 types of elementary matrices. These are matrices which are corresponding to 3 elementary row operations. Yeah? And then upper triangular matrix is one where all entries below the principal diagonal are 0. So let U be an upper triangular or a lower triangular n by n matrix. Then I want to show a determinant is the product of diagonal entries. Yeah. So I have an upper triangular matrix. Let's look at this matrix: A, B, C, D, E, F. Okay. So these entries are 0. These entries are 0, and I have upper triangular matrix. So I look at the entries on the principal diagonal. Yeah? Then what it says is that determinant is the product of the diagonal entries. Okay. So we will let us prove this, but let us also state the results about elementary matrices. So consider the elementary matrix Tijm. That is, we are multiplying ith row by m and adding to the jth row. Okay, when I is not equal to j, then determinant of this matrix is 1. Remember how this matrix looks like. Okay, so let us say T12 of 5. Okay, T12 of 5. So we're adding the first row to the second row after multiplying by 5, and do this for identity matrix. So this is the identity matrix, and we perform the row operation, that is adding 5 times the first row to the second row, and so this will be 1 0 0 5 1 0 0 0 1. So this is my T12 of 5. Okay, so look at Tij of m. So add, this is the elementary matrix where we have the ji entry as m, and other entries are like in identity matrix, and I is not equal to j. Then determinant of such a matrix is 1. Now take the elementary matrix which is obtained by interchanging ith and jth row of identity matrix, then its determinant is -1. This is clear from alternating property. Yeah? Alternating property gives this. Okay. Then look at the row operation where we multiply ith row by a number m, then its determinant is n. So this matrix is upper triangular, ith row multiplied by m, other entries are all 1. So this is an upper triangular matrix, and so if we prove determinant of upper triangular matrix is product of diagonal entries, then this will follow. Okay. So basic fact is about the upper triangular matrices that determinant of upper triangular matrix is product of the entries on this principal diagonal. Okay. Now we want to we will show by induction on n that determinant of A is, look at the nth row, expand by the nth row. Okay, if you take this n by n upper triangular matrix, I want to expand by the nth row. So I proved determinant function, existence of determinant function by using the first row. In the same way, I can use the last row of a matrix. Then when I use the last row, then according to the signs, I will have minus 1 to the power n plus 1 times un1 determinant of un1. Then this will be determinant of un2. Finally, this is determinant of unn. Okay, but if you have upper triangular matrix, in the last row, all these are 0 except for unn. Okay, so only this term survives. Other terms are 0. Okay, so we just get determinant of u equal to this. But unn, what is unn? Unn is obtained by deleting the last row and the last column. If you delete from upper triangular matrix the last row and last column, again you get an upper triangular matrix. So apply the same formula for this. So unn came out. When I apply determinant of unn, there will be a sign, and un minus 1, n minus 1 will come out. That is the entry on n minus 1, n minus 1 entry of u. So now these signs have to be taken care, and I leave it for you to think about this, that the signs will all multiply to 1. Okay. So determinant of a upper triangular matrix is product of the diagonal entries. Okay, product of diagonal entries. Or we can apply the same principle to lower triangular matrices. Then we will expand by the first row. We want to prove the same result for low triangular matrices, that determinant of a low triangular matrix is product of diagonal entries. You expand by the first row and use induction, and you will come out with the same fact that the product of a determinant of a low triangular matrix is product of diagonals. Okay. Now these facts, they follow from this first fact, because these elementary matrices are either upper triangular or lower triangular. Okay. All elementary matrices are either upper triangular or lower triangular. So the three facts about elementary matrices follow. Okay. So if the third operation changes determinant to m, that is, if I multiply ith row by m, then I have a upper triangular, I have a diagonal matrix whose entries are 1, 1, 1, and the ii entry is m, and therefore determinant of this upper triangular matrix is simply the product of diagonal entries, which is m. In the third part, determinant of a matrix which is obtained from identity matrix by interchanging ith row and jth row, that by alternating property is determinant is minus 1. And first, the second part follows by the fact that it is an upper triangular or low triangular matrix. So its determinant is product, and the entries on the elementary matrix E are all 1 on the principal diagonal. So its determinant is 1. Okay. So we know the determinant of elementary matrices. Yeah, we know the determinant of upper triangular matrix, and then we can find determinant of any matrix using the either any row or any column. Okay, so that gives us enough techniques to calculate determinant of a given matrix. But many times a matrix is written as a product of two matrices, and let us prove that determinant of product is product of determinants. Now, if you use a formula to prove this, you can say, okay, let us prove this by 2 by 2. So determinant of a 2 by 2 matrix, I know it has 4 terms. I mean, it has one term, right? Determinant of x, y, z, u is xu minus yz. Okay? So I know determinant as a formula, but it has n factorial terms. If it is n by n matrix, determinant of a n by n matrix has n factorial terms. So if you just plug in into the formula, it becomes a very complicated thing, but it will check. Ultimately, it will check. Now, I want to give you a conceptual proof. Okay? without computing the determinant. We can show determinant of product is product of determinants. Yeah, we will simply show that the two sides are determinant functions on n by n matrices. So A and B are n by n matrices. AB is an n by n matrix, and determinant is a function on n by n matrices. The left hand side is a function on n by n matrices, but we are looking at product. Right hand side is product of two determinant functions. We will show that they are one and the same. Okay. So we want to show that determinant of product of two matrices is product of determinants. Okay. So we know this fact from multiplication of matrices that if I want to multiply two matrices A and B, then ith column of A times B is obtained by multiplying A with the ith column of B. Yeah. This fact I proved earlier, that ith column of A times B is A multiplied with the ith column of B. Okay. So we will show, therefore we prove that the AB is nothing but this matrix whose column vectors are AB1, AB2, ABN. Okay. And we want to show that this determinant function is determinant of A times determinant of B. Okay. Now here comes the non-trivial step in the proof. So look at this. Okay. Keep A fixed. Define a new function on the space of n by n matrices f b1, b2, bn. B is now a varying n by n matrix. A is fixed, and I define this function f as determinant of ab1, ab2, abn. What is this? This is just ab. Okay, so I'm keeping A fixed, and I'm defining a function on the space of n by n matrices. F of B is equal to determinant of A times B. Okay, I will show that F is multilinear alternating. The function is alternating. Why? Because suppose two column vectors of B are equal, then two column vectors of this matrix AB are also equal. Bi equal to Bj, Bi equal to Bj, then this has two equal column vectors, and therefore this is 0. So F is alternating because determinant is alternating. Yeah. Now I will prove the multilinear property. So suppose C is a n by 1 column vector and take any scalar A, and I am proving multilinear property. So kth column is Bk plus AC. I could have taken A Bk plus alpha Bk plus beta C, but the proof is the same. So here is my matrix. In the matrix B, I am replacing kth column by Bk plus AC. So that is by the definition of F is determinant of AB1, A times Bk plus AC, ABN. Okay. Now A times Bk plus AC by properties of matrix multiplication, it is this matrix, this column vector. Okay. I apply multilinear property of determinant function. Now this is determinant function, so I can separate A, Bk and A times AC, and I get determinant of AB1, ABK, ABN, and determinant of AB1, AAC, ABN. This A comes out again by multilinear property, and therefore this is equal to FB1, B2, Bn plus A times FB1, C, Bn. So F is multilinear. So F is multilinear, so any multilinear function, we have proved that it is a scalar multiple of determinant function, where the scalar is the value of the function on identity matrix. So F on B1, B2, Bn must be determinant of B1, B2, Bn, and F of E1 up to En. But what is F of E1 up to En? F of E1 up to En is determinant of AE1, AEN by our definition of F. But AE1 is A1, the first column vector, AEN is the last column vector. This is determinant of A. So value of F on identity matrix is determinant of A, and therefore this becomes determinant of A. This is determinant of B, and therefore this is the determinant of AB. Yeah. So I didn't apply any formula for determinant of matrix. I simply constructed a function which is multilinear alternating, and used that this multilinear alternating function is a scalar multiple of the determinant function. and then I use the formula for f to find out its value on identity matrix that turned out to be determinant of A, and that gives me determinant of A times B is determinant of A times determinant of B. So this is the beauty of the axiomatic method, that complicated proofs become simpler if you follow axiomatic approach, because we have proved that determinant function is unique. Any function which is multilinear, alternating, and normalized is uniquely determined. So to prove some formula for determinant, I will simply use this fact that the given formula has three properties, and therefore it must be determinant of the given matrix. Okay, so that's the idea behind getting these simpler proofs. Last slide, determinant and invertibility. So let us quickly check that we can use determinants to test invertibility. This is not a practical criterion. Yeah? Invertibility of a matrix is checked by using Gauss-Jordan method, that find the row canonical form. If the row canonical form of a n by n matrix is not the identity matrix, the matrix is not invertible. If it is invertible, then the row canonical form must be identity matrix. Okay, so let us see that determinant can also be used to check invertibility if you have access to the formula. Okay, yeah. So Vecha Prasanna is worried about proofs. Okay, so let me tell you, proofs will not be asked in exam. Exams will be always problem oriented. But in order to be good at solving problems, you must understand the proofs. Yeah? You must understand the proofs. That's what I expect, that you look at the class notes and read the same material from the textbooks and be clear that you understand the proofs. So this proposition says that if A is invertible, determinant is not zero, then determinant of A inverse is 1 over determinant. And if determinant is not zero, then A is invertible. So we are saying that a matrix is invertible if and only if its determinant is not zero. And if it is invertible, determinant of A times determinant of A inverse is 1. So they are reciprocals of each other. Okay. If AB is I, then A is invertible and B is equal to A inverse. We have proved this before, but here is another proof using determinants. Okay, so let's look at part 1. It says that if A is invertible, then determinant is not zero. So if A is invertible, then I have A times A inverse is identity. Determinant of product of two matrices is product of determinants. So it says determinant of A inverse times determinant of A is 1. And therefore, determinant of A and determinant of A inverse, they are reciprocals of each other. Yeah. Now, part 2, we assume that determinant is not zero. We want to prove A is invertible. So suppose A is not invertible. Yeah. If A is not invertible, then there is a non-trivial solution to AX equal to 0. In characterizing invertible matrices, I proved this equivalent formulation of invertibility, that AX equal to 0 has only trivial solution if and only if A is invertible. So if A is not invertible, there is a non-zero column vector, so that AX equal to 0 and this is equal to 0. And that says that now one of the xi's is not 0 because this is a non-trivial solution of AX equal to 0. And so I can suppose x2 is not equal to 0. I can use this equation to write down a formula for A2 as a linear combination of other column vectors. So some column vector of A is a linear combination of other column vectors of A, and therefore when I write the determinant by multilinearity and alternating properties, we will see determinant is 0. If one column vector is a linear combination of other column vectors, just use alternating multilinear property to see that determinant is 0. Part 3, if AB is I, then A is invertible and B is A inverse. So if AB is I, take determinants. So determinant of A times determinant of B is 1. So determinant of A is not equal to 0. Determinant of B is not equal to 0. So A is invertible by part 2. And so B is equal to A inverse A times B. And that is A inverse AB. AB is identity. So this is A inverse. So B has to be A inverse. Yeah. Okay. So now we have two proofs that whenever AB is identity, just this one equation rather than B A equal to identity, if we just have one equation, then it implies that A is invertible and B is the inverse. And invertible matrices are exactly those whose determinants are not equal to 0. Okay.